All right, hello students. So today we're going to talk about the uh, review that we did for multiple choice on the My AP. There were four problems that we were really weak on as a whole, and they were numbers 3, 4, 5, and 6. So number 3 was the one that gave most people a problem. So let's discuss this. Here you're given a table of values, x values and the y values for the function f of x at those specific x values. And it says selected values of a differentiable function f are given in the table above. What is the fewest possible number of values c in the interval 0 to 11, so 0 to 11, for which the mean value theorem guarantees f prime of c equal 4? So we're talking about the mean values theorem. So once they say that, then the first thing that needs to come to your mind is recalling the mean value theorem flashcard. What is the mean value theorem? So mean value theorem states that if f is continuous, so remember that it has to be continuous on your closed interval, and it's differentiable, then there exists a c in the interval a to b such that when you take the derivative of c, that means the slope of the tangent, it is equal to the slope of the secant. And I added this on, which is your change in y over change in x. I added that on just specific for this problem here. So how we're going to do that is we're going to look at our table. We don't know what the function f of x is, but we do have certain values. And with that, I can find the change in y over change in x for different little intervals here. So if I look at my first interval, there's my change in y, change in x. My first interval, I can see that my rise was plus 8, and my run is plus 2. So if I do change in y over change in x, 8 over 2, I'm going to get 4. So since this function is differentiable, therefore it must be continuous, then there's got to be a c in between 0 and 2 where the slope of c is equal to 4. That's what the mean value theorem states. Now let's proceed through the rest of this table. Here's the next change in y is plus 12, and the change in x is plus 3. So if you do your change in y over your change in x, you're going to get 4. And for the next one, it's going to be 11 over 2, which is not 4. And then the last one is 13 over 4, which is not 4 again. So the least number of values that will have a slope of 4 is 2. And that is right here, in between 0 and 2, and 2 to 5. All right, number 4 was the other problem. It says the mean value theorem can be applied to which of the following functions. So this is just asking if it can be applied. So if you remember in the last slide, in order for mean value theorem to be applied, the function must be continuous and differentiable on the given interval, which the given interval here is negative 5 to 5. So for the first function here, for the first function here, you see that it's a rational function, and so there's most likely some asymptotes, and you have vertical asymptotes whenever sine of x equals 0. Therefore, when is it going to equal 0? That would be when x is equal to 0, or plus or minus pi, or plus or minus 2 pi, etc. If you remember, wherever sine equals 0. And so at least 3 of these values lie within negative 5 to 5. And that would be specifically 0, plus or minus pi, because that's 3.14. So I have negative 3.14 and positive 3.14. 2 pi is 6.28, so it would not lie within that interval. But here I've already got 3 values of x. That is not continuous. And so since it's not going to be continuous there, you can't apply the mean value theorem. If you look at B, this one's got a jump discontinuity at x equal to 1. You might remember how to do this problem. We practiced this kind of problem when we were doing limits. When you approach x from the left, you would have y values that were negative, and if you approach x from the right, if you approach 1 from the left, you would have -1. And if you approach 1 from the right, your y values would be +1. And so that would lead to a jump discontinuity at x equal to 1. So part C, it has vertical asymptotes, but the vertical asymptotes are at ±6. Therefore, this function is continuous on -5 to 5. So now that it's continuous, is it differentiable? Is there any x values that would make this not differentiable? And the numerator is a polynomial, the denominator is a polynomial. So since they're both polynomials, it would be differentiable everywhere. So therefore, this function is continuous and differentiable on the interval of -5 to 5. And the last one has vertical asymptotes at ±2. Therefore, it's not continuous on this interval. So the answer would be C. Number 5 is similar to a problem that we had on our My AP questions last week, and we struggled with this one. And again, we struggled with this one. So this is something that we need to make sure that we practice and review, so that should it show up, this type of concept on the AP test, that we would do very well. So this is an interesting limit problem because it's a function of f of x, f of x, as x approaches -1. So you're taking the function of another function, which happens to be the exact same function. So we're using this graph twice. So the first thing is, let's look at as x approaches -1. When you put -1 into here, into this x, we're looking at f of x, the inner f of x. So when we do that, let's look at -1. As I approach -1 from the left, my f of x is approaching 3. And as I approach -1 from the right, it's approaching 3. So as x approaches -1 of this, our f of x is now approaching 3. Now you'll notice that here I wrote this as x approaches 3 from the left. Now why did I specify from the left? If you look, as we approached this y value 3, we approached 3 from below it. On the left and on the right. Both times as we approached 3, we approached from y values that were less than 3, not greater than 3, which would be above. So now that this y value here is now turning into an x value, so I can apply my limit to this outer f of x, we need to see that we are really approaching this from the left, or values that are less than 3. And so that's why I rewrote this limit expression to be x going to 3 from the left of f of x. And so now when we look at this expression, and we look at our graph, it is approaching -1. And so this is -1. And the answer would then be, I didn't write the answer, but the answer is C. All right, the last problem is this one here. It says the graph of f double prime, the second derivative of the function f, is shown above on the interval of 0 to 6. Which of the following could be the graph of f? Well, what information can we get from the graph of f double prime? f double prime means the second derivative of f, and the second derivative tells us about the concavity of f. So when I look at this graph, the y values of the second derivative of f represents the concavity. So now we want to analyze these y values right here. So what I did is I drew a number line. And I marked off 1 and 4 because those seem to be important, because that's when the second derivative is 0. We are looking at the y values. So the y value of the second derivative of f is 0. So now, to the left of 1, or at least from the origin to 1, the y values are negative, which means that f is concave down on that interval. On the y values between 1 and 4, they are positive because it's above the x-axis. That means the second derivative is positive. So therefore, f of x must be concave up on the interval of 1 to 4. And then lastly, from 4 on, the y values are negative, which means that f of x must be concave down on that interval after 4. So what does that mean for x equal to 1 and x equal to 4? That means that they are inflection points. That's where they change concavity. So at those points, it needs to change from concave down to concave up, or concave up to concave down. So if we look at option A, the interesting thing here, at 1, it's doing something funky. It has a slope of 0, and it is concave down, and it has a relative max. Now that does not match up with what we have here, because at 1, it's supposed to be an inflection point, which means it doesn't have concavity. It's supposed to be changing its concavity. So right here, it's not changing the concavity, it is concave down. So that means the second derivative should be negative at 1, which it's not, it's 0. So A is not an option. Same reason B is not an option. Here at 1 and at 4, they are relative minimum and maximums. And at 1, it's saying it's concave up, and at 4, it's saying it's concave down, which 1 and 4, again, do not have concavity. Now, C and D are left. So, if I look at C, if I follow this curve, you can see it's concave down to about here at 1, and then here it's starting to change to concave up. And then it's going to change its concavity again to concave down. So down, up, down, concave down, up, down. It looks like it could be C. So let's just verify if it is by looking at D. We see that it's concave down, then it's up, and then it's down, and then it's up, which means it changed its concavity way more times. Let's see, 1, 2, 3, 4. We have 4 changes in concavity, where here there's only 3. So therefore, it's got to be C. And there's your answer. All right. Well, I hope you understand, and let me know if you have any questions. Thank you.